We have already seen that a hyperbola is the set of all that points in a plane such that the difference of their distances from two fixed points in the plane is constant. You have also learned about the parts of a hyperbola, like its two foci, two vertices, center, transverse axis, and conjugate axis. We also derived the relationship b square is equal to c square minus a square, where c is the distance of a focus from the center, a is the length of the semi-transverse axis, and b is the length of the semi-conjugate axis of a hyperbola. We also observed that the difference between the distances of any point on a hyperbola from its foci is equal to the length of the transverse axis of the hyperbola. Eccentricity is an important concept associated with all conic sections, including a hyperbola. It is a measure of the deviation of a conic section from being a circle. The eccentricity of a hyperbola is denoted by E and is equal to the ratio of the distance of a focus from its center and the length of its semi-transverse axis. From the expression for eccentricity, we get C is equal to EA. Thus, the distance of a focus from the center of a hyperbola is equal to the product of its eccentricity and the length of its semi-transverse axis. If we consider a hyperbola with its center at the origin and its transverse axis along the x or the y axis, then there are two distinct possibilities. In the first case, we can have a hyperbola with its center lying on the origin and its transverse axis along the x-axis. In this case, the foci of the hyperbola lie on the x-axis. In the second case, we can have a hyperbola with its center lying on the origin and its transverse axis along the y-axis. In this case, the foci of the hyperbola lie on the y-axis. Let us derive the equation of the hyperbola for case 1 with the center at the origin, the transverse axis along the x-axis, and the foci lying at minus c, 0 and c, 0 on the x-axis. Consider a point P on the hyperbola with the coordinates x, y. Then, by definition, the difference of the distances PF1 and PF2 is constant and equal to 2a. Let this be equation 1. We already know the formula for calculating the distance between two given points. Using the distance formula, we get distance PF1 is equal to under root x plus c whole square plus y square. Let this be equation 2. Similarly, using the distance formula, we get distance PF2 is equal to under root x minus c whole square plus y square. Let this be equation 3. Let us substitute the values of PF1 and PF2 from equations 2 and 3 in equation 1. Rearrange the equation. Square both sides of the equation. On simplifying, we get under root x minus c whole square plus y square is equal to c upon a into x minus a. Squaring both sides again and simplifying further, we get equation 4. substituting the value of a square minus c square as minus b square in equation 4, and simplifying further, we get x squared upon a square minus y squared upon b square is equal to 1. We can say that equation 5 represents the given hyperbola if the coordinates of point P as derived from this equation satisfy the geometrical condition PF1 minus PF2 is equal to 2a. From equation 5, we get y square is equal to b square into x square upon a square minus 1. Substituting the value of y square from equation 5 in equation 2 and simplifying, we get PF1 is equal to a plus c upon a into x. Substituting the value of y square from equation 5 in equation 3 and simplifying, we get PF2 is equal to c upon a into x minus a. Substituting these values of PF1 and PF2 in equation 1, we see that the geometric condition is true. Thus, we can say that point P lies on the hyperbola represented by equation 5. The equation x square upon a square minus y square upon b square is equal to 1 is the standard equation for a hyperbola with its center at the origin and the transverse axis lying along the x-axis. Similarly, we can derive the standard equation for a hyperbola with its center at the origin and the transverse axis along the y-axis. The equation is y squared upon a square minus x squared upon b square is equal to 1. These two equations are called the standard equations of a hyperbola having its center at the origin and the transverse axis along the x or y-axis. Here, we can make some interesting observations. Observe that if the coefficient of x square is positive, then the transverse axis of the hyperbola lies along the x-axis. Similarly, if the coefficient of y square is positive, then the transverse axis of the hyperbola lies along the y-axis. Note that both the standard equations of a hyperbola contain even powers of x and y. Therefore, a hyperbola with its center at the origin and the transverse axis along either the x or the y-axis is symmetrical about both the coordinate axes. What this means is that if a point px, y lies on the hyperbola, then points minus x, y, x, minus y, and minus x, minus y also lie on the hyperbola. A hyperbola in which semi-transverse axis A is equal to semi-conjugate axis B is called an equilateral hyperbola. The standard equations of a hyperbola also specify certain conditions for the position of its curves. Rearranging the standard equation of a hyperbola with its center at the origin and the transverse axis along the x-axis, we find that the modulus of x upon a is greater than or equal to 1. This implies that for any point on the curve of the hyperbola, the value of the x-coordinate is less than or equal to minus a or greater than or equal to a. Thus, no point on the curve of a hyperbola with its center at the origin and transverse axis along the x-axis lies between the lines x is equal to minus a and x is equal to A. Similarly, rearranging the standard equation of a hyperbola with its center at the origin and the transverse axis along the y-axis, we find that the modulus of y upon A is greater than or equal to 1. This implies that for any point on the curve of the hyperbola, the value of the y-coordinate is less than or equal to minus A or either greater than or equal to A. Thus, no point on the curve of a hyperbola, with its center at the origin and the transverse axis along the y-axis, lies between the lines y is equal to A and y is equal to minus A. A line segment passing through a focus and perpendicular to the transverse axis, and with its endpoints lying on the curve of a hyperbola, is called its latus rectum. Since a hyperbola has two foci, it has two latus recta. Consider a hyperbola with its center at the origin and the transverse axis along the x-axis and latus recta AB and CD. Let length AF2 be L. If C is the distance of focus F2 from center O, then the coordinates of point A are C, L. Recall the standard equation of a hyperbola with its center at the origin and the transverse axis along the x-axis. Since point A lies on the hyperbola, its coordinates must satisfy the standard equation. Substituting the coordinates of point A in the standard equation of a hyperbola and simplifying, we get L is equal to B square upon A. Since the hyperbola is symmetrical about the x-axis, distance AF2 is equal to distance F2B. Hence, the total distance AB is equal to 2B square upon A. Distance AB is the length of the latus rectum. Thus, the latus rectum of a hyperbola with its semi-transverse axis equal to A and the semi-conjugate axis equal to B is given by 2B square upon A.